HVAC 360 is brought to you today by moms, who remind us not to let your babies grow up to be cowboys, but if they grow up to be engineers and contractors, that's just fine. Moms always know best. Thanks, Mom. What's up? Welcome back to episode number 83. Matt Nelson here, your host for HVAC 360, helping you go further and faster in the field of HVAC. In these podcasts, I share about stories, interview experts like today, and serve up the meat and potatoes to bulk up your HVAC knowledge. Now, if you're new here, or if this leaves you wanting more information, just go to my website at hvac360.com and subscribe to my list. And you'll get additional perspective served up to you fresh on a weekly basis. So what's up for this week? Well, we're going to talk about what controllability is and how that affects building performance. To answer these questions and more, we jump to the other side of the pond to speak with Graham Smith, a CIBSE Fellow and an expert on controllability. All right, first off, a little fair warning. I've had the gnomes here at HVAC 360 HQ working pretty hard to correct the audio on this episode, but it still sounds like I'm talking to Graham down a well. But there's not an annoying buzz in the background that came across when we were speaking across the pond. Really would love to blame Skype for this one, but I think it was just the types of system we were using. So, critical. This is really, try to get through it, I guess, because this topic is really becoming more and more relevant as systems become more complex. It really centers around central plants, and we're not talking like big industrial-sized central plants. It could be a couple of boilers, it could be a chiller. It really is critical to setting up your system. And really, if you really nerd out on this and get a lot of education, it could be a nice niche if anybody wants to make a real business out of it. Seems to suit Graham just fine. So please stick around after the interview, and I'll share my 3 top favorite takeaways from the conversation. So let's cut to the tape after this brief word from our sponsor. All right, hey, we're here with Graham Smith of Birling Consulting. How are you doing today, Graham?
Fine, thank you.
Hey,
and snow is gone.
Well, at least for one of us. So, just out of the gate, I have this curiosity. I know that you're involved in energy efficiency with building performance, and I'm involved with commissioning. So can you explain a little bit about how commissioning exists in the UK as part of the construction process?
Right. Well, one of the main problems is the end of the construction process, and that the time available gets squashed. There tends to be commissioning specialists who do the system balancing, flow measurement, and then there are control specialists or manufacturers who commission the control systems, and manufacturers of boilers, chillers, and so on who commission the appropriate bits of kit. There are CIBSE guides for management of commissioning. Unfortunately, they very rarely get actioned correctly. So it tends to be a last minute thing, and everyone wants to tick boxes and get the system handed over. Which is often it's not done as well as it should be done.
Okay. Now, I guess how would you describe Birling Consulting? I mean, what kind of work do you do? I was a little presumptuous, but how would you describe it?
Basically a specialist consultant. I mainly work with other consultants, assisting them to design systems so that they can be commissioned, so that they are controllable systems, and write decent BMS specifications for them. I also get involved in doing mechanical design and management systems. I originally started as a controls engineer and ended up as a project manager for specialist buildings. So I was in charge of the overall design team, including architects, civil, structural engineers, and all of that. Since going back to working as a specialist, then primarily I get involved in control systems, commissioning, sorting out problems, resolution of issues with the systems. I've just been involved in a 1 megawatt BioMass system that didn't work properly. It was stopping the handover of a £25 million project. There were some hydraulic issues which we've resolved, and we've now reset the control system up so that it works in a sensible mode. The previous control system commissioned by the BioMass specialist was not very satisfactory, to say the least.
Is it a problem with the knowledge of the integration between the systems, or why is the system set up by an expert not working properly? What are the problems that happen there?
Right, I think there's a number of issues, and controllability of systems is poorly understood. Which relates to the size of the plant. Often boilers, chillers, and so on are oversized, which can cause a number of issues. Turned down is not adequately specified on those bits of kit at times. There's inadequate support, from specialist companies, where you get biomass boilers, CHP systems. A lot of those companies don't provide adequate support to designers to give them the right information. I was involved in a CHP system a few years ago, and I happened to be on site when they were installing it. I was glancing through the installation and got the manual, and on page 100 I found something that was critical to the design of the system. It wouldn't accept return temperatures over 70 degrees C, and this had been sold on the basis of an LTHW system as the lead heat source, where it was 82 flow, 70 to return. And therefore the CHP would have never worked under those circumstances. Fortunately, we had a swimming pool, we had a heat exchanger we could connect it to and get the right temperatures, and we did a very rapid redesign and got the system working. It's worked very well ever since. But information from manufacturers can be an issue. Hydraulic design is often a problem. People don't understand how to make systems controllable. So it's often fairly simple once you understand the issues.
I think that a lot of people, at least how you describe it, and if I can kind of maybe simplify it to, I think a lot of people understand system effect as it applies to a fan. And I think when you're talking the hydraulics with the oversized plants, you're referring to how it operates through, the different conditions that it's going to be exposed to, and the different conditions that may not be what you've set up the design to do. It's not a design day condition. Obviously, they have to operate throughout the year, and what kind of conditions are going to be seen, what kind of flows, pressures, temperatures, and things like that. Am I getting it right?
Absolutely. With a lot of mechanical designers will consider design conditions, middle of winter or middle of summer, but 95% of the year you are not at design conditions, and the plant is operating at part load, and this part load performance is where you often get the problems. Sometime, or in the past, these tend to have not been noticed as much. But nowadays, with bivalent systems, with biomass, CHP, heat pumps, people are looking at utilisation of the low carbon heat sources and finding that they're not giving the performance they should. I looked at two biomass systems on one site and the utilisation was 13%. Often, I've seen quotations from this biomass manufacturer for another site. The energy produced by the biomass system in his calculations for payback was far more than the actual site used. So there's a lot of misinformation out there, and manufacturers, specialist suppliers aren't necessarily doing themselves a favour in the way that they present their information.
Now, obviously we've gotten biomass boilers you're talking about, or is that am I getting that right? Biomass boilers that you're referring to, or just biomass generators?
Biomass boilers.
Okay, and then CHP, that's the combined heat and power.
So a gas-fired combustion, internal combustion engine providing heat and electricity. So,
right.
Which they can work very well. Often, the specialist supplier will try and supply something that's larger than is necessary, and that's often where the problems start. And then hydraulics, and then temperature limitations. I looked at some the other day, CHP systems from one manufacturer. We were looking at different sizes to try and optimise the size for a project. And each different size of CHP system had different temperature limitations. So you've got to consider that in the hydraulic design. Usually you can overcome the limitations provided you know what they are and how to tackle it. Which often, sometimes you need heat exchangers, buffer vessels, thermal stores. There's a lot required to actually understand to make the system controllable.
Right. So, I mean, when you have the system and it is, I mean, these are not standard systems. They're used for high efficiency kind of operations. I think that at least most of the buildings don't have these type of systems. But you would think that... Go ahead.
They're becoming more increasingly an increasing requirement in the UK to incorporate these into designs, and then there's a big push for community heating, heat networks which are providing heat from a central source. The idea there is that the central source is more efficient than you can include CHP or biomass or heat pumps, which are a low carbon heat source. Unfortunately, the way a lot of the systems are designed and operated doesn't give you the advantages that they should provide. Especially where people try and do value engineering and cut out essential features or reduce the design standards.
Do you think that the manufacturers intentionally upsell, increase the size of equipment because they know that it may not be operating exactly how they have, exactly how the engineer requires it, so that they're not undersized, so that at least they're getting, whatever output they need?
That's certainly one reason for doing it. Unfortunately, it then causes other problems. If you have a heat network which is a high differential temperature, so we're trying to create high differential temperatures, low flow rates on the secondary side, so it reduces pumping energy, and you've got a low temperature, so the condensing boilers will work in condensing mode. But if you have oversized plant on the primary side, then normally the boiler will have a fixed flow rate. Therefore, if you have a low loss header, then you've got recirculation on the primary side, and immediately you've got higher temperatures coming back to the condensing boiler, and it will never work in condensing mode. I've been doing a lot of work with variable flow boilers recently, including thermal storage systems for peak loads on university campuses and that sort of thing. There are ways of making it work, but you need to understand what's required and particularly what boilers you need to make it work. And the same's true with CHP systems, with thermal storage. There's lots of ways of doing things. There's an awful lot of ways of doing them that don't work properly. You can, in some cases, do a workaround and maybe get the control system to do things that may not be ideal, but get the plant to work. But it's much better to get it to work properly in the first place and for it to be a controllable system. But often people don't really understand much about controllability and just like ticking boxes to say they've got BioMass or CHP or a heat pump. There are limitations with that approach.
So the controllability that you're talking about, I mean, obviously, how would you teach that to younger engineers? Where does that come into play?
Well, there's a number of sort of basic things. If Q equals MC delta T, I know that's a common expression in the States. You start with that. If you ask most control engineers what that means, a lot of them wouldn't necessarily know. If you ask most mechanical engineers if that's got any relevance to the control of your systems, they probably also wouldn't know. But you've got to get the temperatures and hydraulics right as a starting point. You've got to understand the characteristics of the plant, how it works under all different load conditions. It's an understanding of hydraulics and an understanding of the plant operation, and then putting those together and then getting an overall control strategy. And the system designer should write that control strategy. Most of the time, controls inadequately specified, in my view. For biomass systems, often there's a sort of line that says the biomass boiler must be the lead heat source, but they don't tell you how it should be the lead heat source, how it's going to work, and how the subsequent plant should operate. Quite often, the systems are designed with temperature-based control strategies, and the individual plant has its own temperature-based control strategies, and the two interact. I use quite frequently heat load-based control strategies, so you're actually looking at the load on the system and then just enabling the boilers or the chillers to come on and off and control under their own package control system. Then you've got a single point of responsibility for the chiller or the boiler to produce the temperature at the designed flow rate and work in a stable manner, and all you're doing is enabling them and disabling them accordingly to load. And in that way you can actually maximise the efficiency of the devices. And so modern chillers and modern boilers are more efficient at low loads. If you can run it at lower load but in a stable manner, then you're improving the efficiency. But you've also got other factors to consider. Recirculation around the primary loop, that will affect the efficiency of the boiler. So on a condensing boiler, for instance. So there's often a number of factors that you need to take into consideration, and plant space can be an issue. If we're doing heat load based control, then we've got to have flow measurement, so you're measuring the flow rate and differential temperature. Often plant space is limited, so space to put in a flow meter with 10 diameters upstream straight pipe and 10 downstream straight, or 5 downstream straight pipe may not be available. So there are other options. I did one the other day where we just use pump speed. It's not ideal, but it works, and it works far, far better than the system that had originally been installed.
So now I guess you have the advantage of having kind of a huge controls background, as opposed to a lot of the design engineers that they've been designing systems.
Yes.
Yeah. So, and I guess just so people know, I mean, controlling a system based on a set point, that's an easy thing. You slap a sensor on a pipe in a well, and you get a temperature that you can control to. But when you're talking about actual, controlling to heat flow, now you're actually adding a differential temperature with a rate of the flow of the whatever medium you're using, flow of water.
It's nothing new. In fact, I believe it originated in the States back in the 1970s. But flow meters now are far more accurate and far cheaper than they used to be. There's a lot of heat meters now being used in the UK and Europe. So these the ultrasonic ones. They do need to be installed correctly. I don't know whether you use heat interface units in the States. They're quite often used here for individual apartments, to measure the amount of heat going into the apartment and provide heating and hot water. They usually incorporate a heat meter, which is an MID approved heat meter for billing purposes. But very often they're not installed straight after right angles in the pipework. They're never going to work properly like that. I've seen them where they seem we've measured the heat in the boiler house, we've measured the heat in the apartments, and there's a difference of about 30%. So it makes a considerable difference how you install the equipment.
Yeah, and in most cases, if I'm looking at a set of drawings where it's diagrammatic in nature and it doesn't reflect the actual installation, so you're relying on the contractor to pick a good point. And typically there is, like you mentioned, there's no good point to put a flow meter in a lot of situations where you have a lot of bends in the pipe. You don't get that, straight run of, 20 feet of pipe.
It's part of the design for controllability. And, if you can't do that, then it may be that you need to take another strategy. As I said, the other day, we were trying to get some boilers to control on heat load. We managed to sort out the BioMass boiler, but the gas-fired boilers, the control system was complete garbage. So we've actually simplified it, and we just we enable the primary boiler, the lead gas-fired boiler, on temperature. If the biomass boiler is not topped up the heats adequately on the return of the system, and the second boiler we purely enable on pump speed. So if the distribution system is above 80%, it brings the boilers on and drops off below 70%. It's not ideal, but there are heat meters in the individual buildings, but they couldn't solve the communication problem to those. So it's always worth, if you're relying upon remote sensors, it's always worth having a backup strategy, either in case of communication failure, or if in this case we couldn't get it working during the time available, to implement that at the time. But, so there are often workarounds, but it's better to have it work. Have a principle that should work most efficiently in the first place. So I got to ask you, there's a story that about your 15-minute solution. So tell us a little bit about that story. Yes, basically, I won't say the name, but I was working for a large consultancy at the time. The local team, who were located about 500 miles away from where I was, had been working on a building for about 18 months, and their conclusion was it needed a new building management system. This was probably about 15 years ago, and the cost was £65,000 from what I remember, so about $100,000, something like that. I was asked to go and have a look. I went to site, started asking some questions, and after about 15 minutes I reached the conclusion that the primary problem was the deadband between heating and cooling had been set too close, causing the system to was actually overlap between heating and cooling, and which was wasting about a quarter of their energy. So we reset it in one part of the building, which took probably another quarter of an hour, and that seemed to work. And so it didn't need a new building management system at all. All it needed was setting up properly. There was also some sensors that had been were poorly positioned because the partitions had been moved in some of the offices, which is a common issue. It took 15 minutes to find the problem, which saved them $100,000.
Wow. No, I mean, so that's I guess that's a great example of finding things that are just, not only did it save them, money, but I'm sure it saved them energy too.
Oh yeah, they were wasting their energy bill had gone up by 25%.
Now,
so somebody had been fiddling with the settings. They're probably trying to control it closer. In fact, I had two projects I was asked to look at last year. One was the production facility, a large aeronautical production facility, and there they had oscillation between heating and cooling, and it was going all over the place. And basically, they'd set it up as proportional control only on the research units within the space. So I set it up as a P+I control loop, set 5 degrees proportional band, 5 minutes or something interpolation time, and it just ran nice and stably. I recommended 1.5 degrees deadband. They insisted on making that 1 degree to start with, but then changed it later in the day to 1.5 degrees because the units were interacting with each other. So there's about half a dozen units within the same space. So it's all tight control. So that one we were very successful day on site. They paid out an awful lot for the commissioning of these. I put a bill in for about 5% of what they'd paid originally for the systems to be commissioned poorly. I'd solved the problem, put the bill in for 5%, and I said, "Oh, we didn't expect a bill that big." And then 2 weeks later, I was called into some other plants on a laboratory which had exactly the same problems. Unfortunately, the system we couldn't get working. They had on-off reheats, and the reheats were inadequately sized for the dehumidification load because it was a high proportion of fresh air, and we actually had to redesign the complete system, and I had to take out the complete installation and put in a new one. And
now, is that a case where you have the design was, here's the design day, and it has to operate kind of in those those intermediate zones?
Yeah, basically, there's a fairly small window. If you look at the psychometric charts, there's a small window of acceptable conditions. That was a laboratory. And to achieve those, you've got to look at the amount of reheat you need and what controls necessary within that. So you have it all comes back to having a controllable system. The first example, the system was controllable but hadn't been set up right. The second example, the system was not controllable. We went through endless loops trying to find replacement research units that would go into the space. In the end, we couldn't find any that would actually achieve the conditions that we wanted, and had to put an air handling unit outside. The contractor was partly driven down that route by the clients who didn't want plant outside in the first place. Didn't want more space being used up, and that can be an issue where people want to put things in a space that's too small. It can have it can create other problems.
Right. So what do you think? I mean, as far as controllability of systems, how many systems? What percentage do you think have been set up correctly?
Very few. Very few of the ones I see. I really hope that what I see is not representative, because I tend to get called into systems that are not working properly to put them right. But there's an awful lot of documentation around about systems that don't work. There's a lot of papers and so on published by people like Bill Bordas. I don't know if you've come across Bill, and also the Neighbours program in Australia. But a lot of the time things can be improved considerably by just going back and doing basic things. But also a lot of what I've found is quite a lot of the time hydraulics need to be changed. It's a BioMass system I've recently been working on, where we made some changes to the system hydraulics. Although the hydraulics as they weren't dissimilar to current, to the CIBSE guidance, but because of the boiler sizes, it didn't. There was too great an influence of gas-fired boilers. So again, it's a question of understanding all the influences upon the system, particularly at part load conditions.
So I'm assuming that there's probably a bunch of systems out there that are just energy inefficient, even though they kind of nobody realizes that there's a problem. Those aren't the systems that you're getting called about, but those are the systems that are out there, and I'm probably sure that there's maybe a small minority of systems that may be working properly.
Yeah, I think that's true. So I think a lot of systems don't work as efficiently as they should. There are quite a few instances that have been reported of buildings using 3 times the energy that they should. I was asked to do a report on one sort of a year or so back. Very large. I think it's a £90 million project. So 130, $140 million. Could we do a thermal analysis of it, do a report, and get everything done in the space of 2 weeks? It's a physical impossibility, even if I'd had a team of 10 people to do it. And I think that shows the client's understanding of what the issues are. I suspect there are a number of reasons why that building doesn't perform. I think some of the thermal modelling may be a little bit optimistic on the way things perform. Certainly in older buildings, air leakage is a problem, air infiltration. I was responsible for a building 10 or 12 years ago that was on the top of a cliff top, and wind speeds of over 100 miles an hour have been recorded. I think 136 was the maximum. We went to great lengths to make sure it was airtight. and it worked. And we did everything that was necessary to make it controllable. A combination of 2 and 3 port valves for the variable flow system. I was back on site 2 or 3 years ago, and they're still happy with it. If you do it properly in the first place, it makes a considerable difference.
Now, do you think that is there as far as like governmental mandates, excuse me, getting a grade for your building, like energy and an energy grade, is that something that's being done in the UK? Is that something that may be kind of tipping owners off to saying, hey, you know what, my building, is using a lot more energy than the building next door?
Yeah, there are public buildings have to have certificates. Commercial buildings, there are various schemes in place. Some of them are more effective than others, and again, I think a fair bit of it is it's a little bit of tick box engineering to some extent. The building regulations have specific fan performance details, have specific requirements on certain things. I have certain views on them. I think they could be significantly improved. Again, I think some of it it reflects a lack of understanding of what makes the buildings work.
Right. So we're not there yet, I guess. No. So I guess what can be done, is the solution to educate the engineers, educate the controls contractors, educate the owners. Where would the best use of education come about?
Well, I think it's a combination. I think I don't think there's one solution. I think the first step is to educate the systems designers. So, with the GR40, I was involved as primary author for that, for the Energy Efficiency Best Practice Programme 25 years ago, and with CIBSE and Brexu at the time, we did a programme of lectures around the country to try and educate systems designers and controls engineers on how to make systems work in an efficient manner. And I think that had an influence. There's still people who use that guide to this day, but it is now well out of date. So we need improved guidance. There's a lot of information out there. There's lots of guides on certain things on the BioMass guide. I was involved with the CIBSE. We did put a fair bit in on controllability of systems and system design, but there's very little in other guidance. So, engineers need to have that information, need to have that guidance. There is very little documentation out there at the moment. I've started writing a book, but how far I get with it, I don't know. I may do it when I retire, but might have better things to do. If somebody can sponsor me in the meantime, I'll write it. I think that is desperately needed. More information. I think it's education of the systems designers to design a control system, better education of the systems integrators, controls contractors to understand how to make things work. I used to do training for some of the controls companies some years ago, and what I concentrated on was sort of telling them how to control the systems and what's the important factors, rather than how to set up a P+I loop. Because I should know that, although some of them seem to have forgotten. And then the building user also needs education on what to do and what not to do. So how, what to touch on his system, what to leave alone, And the number of times partitions get moved but sensors don't is amazing. So they need to be educated. If they make changes, then they need to consider the effect on systems. I've had people in sports centres change meeting rooms to gyms, but which requires a higher fresh air rate, but they weren't aware of it. I've also had an office that we designed for 6 people to occupy, so fresh air for 6 people. I once counted 26 people in there. So it's not just the building designers. The architects need to have a better understanding of spatial requirements for plants. They don't talk. Even when I was managing the architects on projects, I had difficulty in getting them to allow enough space so that we could put air handling units in, that sort of thing. So sometimes the client pushes for maximum spatial utilisation, which is understandable because that affects his bottom line, but he doesn't appreciate the implications of that.
Yeah, I think that's extremely difficult for architects to get a handle on, because, and I don't think that necessarily systems designers stand up for themselves enough, because architects tend to have egos when you get to the designer level. Maybe not necessarily the details level, but the designer level. They have an ego. They're the one. They want it to look a certain way, and they're going to try to squeeze out as little mechanical space as they possibly can.
Yeah, I have noticed that. The egos bit.
So, well, fantastic. I mean, it sounds great. I appreciate any last words that you have that you want to.
I think it really needs an effort by everybody. I think particularly controllability is the biggest issue that I see that is not understood properly at the moment, and there is little guidance out there. To me, that is the area that should really be developed in terms of providing guidance to designers. But at the moment, I find very few people understand what it is and its importance.
All right. Well, let's learn more about controllability, everybody. So do your part and help Graham out with this crusade of his. So. All right, thanks for your time, Graham. I appreciate it.
Okay, thank you very much.
All right, we're back. Thanks again to Graham Smith with Birling Consulting for taking the time to chat with us. Check out the show notes for some of the things that Graham had mentioned during the interview, especially since a lot of these CIBSE resources aren't that familiar to most of us in the United States, but they are still valuable resources, even though you probably have to convert from SI to English. So, all right. You can find those show notes back at hvac360.com/83. Since this is episode number 83, I'm starting to do that nowadays. All right. As promised, here are my 3 highlights from this interview. First off, we have the plant sizing and the role of the manufacturers. That was kind of interesting to get his take on how manufacturers, how you can get some variability on understanding and support from different manufacturers. Not everybody's the same. There's some good manufacturers out there and bad manufacturers out there. And even the good manufacturers, don't necessarily always have all the support that you need to fully understand your system. So make sure that you understand your system as an engineer and get that detailed properly. All right, highlight number 2 is designing in controllability. And I really like how Graham had flipped this back on the engineer, saying, hey, you know what? If you were going to have a system, it's more than just throwing a bunch of control devices on a drawing and expect it to work, or leaving it up to the controls contractor to really take over and make it an optimal solution. So I like that aspect. Number 3, heat load for a strategy for controlling the plant. Now, I need to learn more about this, and I think it's really easy as engineers to throw the word optimize around that and really give it just lip service. And I think what we need to do is we need to really understand how systems operate, not just functionally. I mean, they can follow the control sequence, but Graham was getting down deeper, more than just following the control sequence. It was really optimizing, making sure that everything was operating properly, and sometimes it would operate in ways that you wouldn't expect. And it's really hard because, just like system effect, it's hard for an engineer to look at a drawing and say, okay, I'm going to see there's going to be system effect here at these back-to-back elbows, and it's really going to play a lot of havoc. But to understand a dynamic system like a chilled water plant, biomass plant, heating water plant, to understand the whole system, this dynamic system, is really hard because you're just piecing bits and pieces together and really understanding. That's why I'm going to have to go back to the blackboard and really try to understand that one. As always, thanks so much for listening. I hope this was helpful. Again, hey, if you know anybody who's in the building performance or controllability space, why don't you go ahead and share this with them? Not only is that going to be good for your friend, but it's also going to be good for you and building the connection that you two have. So, as I mentioned at the top of the show, if you haven't subscribed to my list, please do so. It's at HVAC360.com. I share weekly goodies there. And if you want to do more, because you haven't done enough already, you can always consider leaving me a review on iTunes. Well, that's it for this episode. I'm Matt Nelson, helping you go further, faster in the field of HVAC. And as always, know what you build and share what you know.